This is the lecture 14. So in lecture 13 we have started discussing that stability analysis of linear time invariant system. So today we'll be discussing one important result, that is that Routh-Hurwitz criteria. Routh-Hurwitz criteria. So in last lecture, what we have seen, the stability of linear time invariant systems can be checked just by looking at the roots of the characteristic equation, and we have discussed that two necessary conditions need to be satisfied. That means whenever a polynomial is given, so suppose a polynomial, say fs, that is an s to the power n s to the power n minus 1. So suppose we have a polynomial and here this one equal to 0. So I would say that this is a characteristic polynomial. So that means whenever an LTI system is described in transfer function form, if we make that denominator equal to 0, then it gives that characteristic equation. So this is that characteristic equation. So now just by looking at the location of the poles, that means for stability, bounded input, bounded output stability or asymptotic stability, both of them are equivalent in case of linear time invariant system that we have discussed in last lecture. The all roots of this characteristic equation should be in the open left half of the complex plane, or all the poles will be lying in the left half of that S plane. So then that system would be asymptotically stable or bounded input, bounded output stable. And we have seen two necessary conditions. That means all the coefficients, these are the coefficients, so they should be with same sign, as well as no coefficient should be absent in this particular polynomial. So these are the two necessary conditions we have discussed. So today we'll be discussing one criterion, and this is very easy to check whether roots of this polynomial characteristic equation would be in the left half of that S plane or on the right hand half. So that means this stability boundary is that imaginary axis, and whether roots are on the right hand side or on the left hand side, that can be checked by using this Routh-Hurwitz criteria. So let us discuss what is that Routh-Hurwitz criteria. First of all, it has some limitations. So Routh-Hurwitz criterion can be applied only for the polynomials which has that real coefficients, and as I now just pointed out, that means the stability boundary is the imaginary axis. We cannot take any arbitrary stability boundary. So these are the two limitations of Routh-Hurwitz criterion. So that is actually a method. This is a method of determining the location of zeros. So zeros, that means that roots of a polynomial with constant real coefficients. So that means if you have some coefficients which are not real, that means maybe complex, so we cannot apply this Routh-Hurwitz criterion with respect to the left and right half of the S-plane without actually solving for the zeros. What is that? So here it says that it is a criterion which is used to check whether the polynomial has roots with respect to the left and right half of that S-plane without actually solving it. So without solving this polynomial, that characteristic equation, this is that method by which we will be able to say that whether roots are on the left or on the right half of that S-plane. That means this is that plane. So this is that S-plane. Here sigma, this is j omega, and this is that S-plane. So Routh-Hurwitz criteria tells us whether poles will be on the right half of that S-plane or left half of that S-plane. And another limitation is this criterion is only applicable to the polynomial with constant real coefficients. That means if the coefficient is a time varying coefficient or complex coefficient, exponential coefficient, we cannot apply this criterion. And this criterion tells us that necessary and sufficient condition for that stability. That means whether roots should be on the left half of that S-plane or not. Using this criteria, we'll be able to decide. So this is a necessary sufficient condition. And what is that condition? That means whenever this polynomial is given to us, that means this is, we say for LTI system, this is that characteristic equation. Then the necessary and sufficient condition, the necessary and sufficient condition that all roots of a constant, again I am writing constant coefficient polynomial, lie in the left half, of, so left half of the S-plane means it says about the bounded input, bounded output, or asymptotic stability of that LTI system. Left half of the S-plane. So that means here we have drawn this particular plane. So this is that S-plane. So whether roots are lying in the open left half of that S-plane or not. So this criteria says that this is the necessary and sufficient condition is that the equations Hurwitz determinant dk. I am going to explain what is that Hurwitz determinant. There are n number of Hurwitz determinant, must all be positive. So this is actually that Hurwitz criteria. So Hurwitz proposed one criteria, that is that necessary and sufficient condition, which is very important. That means whenever one characteristic polynomial is given, then we need to judge whether the roots of these characteristic polynomials are in the left half of that S-plane or not. Because for stability, all the roots should be in the left half of that S-plane. So Harvey's proposed one criteria, and this is that necessary and sufficient condition. That means whenever a polynomial is given, we can form n number of matrices which are called actually Harvey's matrices. So, and the determinant of those matrices, that is called that Harvey's determinants, should all be positive. So for this particular polynomial, so this is that polynomial, you can see here, that is that coefficients are a0, then a1, like that, an to the n minus 1, and the highest coefficient, that is an. So using those polynomials, we can form that some matrices like an minus 1, then d2, this is another determinant. So those determinants are called that Harvey's determinant, an minus 3, and here an and n minus 2, then d3, this is 3 cross 3 matrix, that is a n minus 3, n minus 5, and here in the diagonal n minus 2, n minus 3, here n minus 4, here you have n, and here 0, an minus 1. So I think it is clear from those matrices what sequence we need to follow for forming that Harvey's determinant. And here you can see that general one, that is dn. So dn is that an minus 1, then here n minus 2, here n minus 3, like that. Need to go up to a0, and here we have an minus 3, an minus 5, here an minus 4, n minus 1, like that. So here you would have 0, so we can form those determinant, and according to that criterion, that means the determinant, all of those determinant, that is d1, d2, d3 up to dn, all of them should be positive. So whenever we will be forming that Harvey's determinant, so here where the coefficients with indices larger than n or negative need to be replaced by 0. So here you can see that, suppose this one, so then it would be a n minus 1, then we add plus 1, so that is a n. So then if we add another one, so that is a n plus 1. So you can see that indices larger than n, it would be 0. So that's why this is 0. Like that, we can just form this Harvey's determinant, and all the determinants should be positive. So what we have discussed now, that means whenever a characteristic equation is given and all the coefficients are real coefficients, so then we can form the Harvey's determinants. So these all are the Harvey's determinants. Now the roots of this particular polynomial, will be in the left half of that S-plane if and only if all the determinants are positive. So there is a major disadvantage, that is whenever the number of coefficients are more, that means if this degree is more, or if some coefficients are unknown, that means in case of design actually we need to do that. So in that case, the dimensions of those determinants would be large and the process would be tedious, and also it involves a lot of computational effort, and also it is very difficult to find out the condition for stability. That means all roots of that polynomial would be in the left half of that S-plane for the range of some parameters involved in those coefficients. So it would be very difficult to find. So then Routh proposed one method, one tabular method, by which we can find whether all the Harwich determinants would be positive or not. So Routh proposed one method that is called that Routh table. This is called that Routh table. So using this particular tabular method, we can easily find out whether the roots of that polynomial are in the open left half of S-plane or not. So suppose if we take one polynomial, like say suppose a6 s to the power 6, then a5 s to the power 5, a4 s to the power 4, a3 s to the power 3, a2 square, a1 s plus a0. Suppose we have one characteristic equation like that. So then Routh proposed one method by which we will be able to find whether all the roots are in the left half of that S-plane or not. So the method is as follows. First, we need to write like this, that is s to the power 6. So this is that coefficient. Then we need to write s to the power 5, then s to the power 4, s to the power 3, s square, and s. And then s to the power 0. So that is basically s to the power 1. So these are all the coefficients. And then we have that a6. So need to write a6. Then a4. So this is that method. a4. Then a2. So basically we are writing all the even coefficients, and then a0. And in the next row we need to write a5, a5, then a3, then a1. So in the first step we need to first write this particular column, and these all are for identification purpose. These all are for identification purpose. I would say that for identification purpose. For identification purpose. And here then in the first row we need to write all the even coefficients, and then in the next row we need to write all the odd coefficients. Then we need to follow this particular multiplication method. So here the multiplication would be like this. So we have a5 into a4, you can see here, minus a3 a6 divided by a5, this one. So we define that this particular term as suppose a. So the next term in this row, that means what would be this term? So this term, suppose we write that this is B. So this term would be multiply with this one, then multiply with that one. So if we multiply with this one, we have A5. We are doing this thing, and A2 minus A1 A6 divided by A5. A5 is this one. So the third term is, so this is that term, that means in this particular column. So that is multiply with this one. So that means we have A5 into A0, then multiply with this one. So you can see here that this value is 0. So that means if we multiply with that one, you have minus 0 divided by A5. So then if we do that one, so basically we have A0, only this term. So now, so this row is done. So this is the method you need to follow to build that route table. And then the next one is, so this is that A term. So now multiply with this and then multiply with that divided by this term. So what it would be? It would be, if we multiply with that, that means this one. So that is A3 minus, then this one, B A5 divided by A. Again multiply it and then multiply with this one. So if we do that one, we have A1, this one, minus A0, this one is A5 divided by A. So if we just define just like before, that this one is suppose D and this one is E, and here you can see that means if we proceed again, so that means the other values are zeros. That means if we just proceed here, if we go like this one, and the next value is 0, so that means 0 minus 0 divided by 0. So that means we need not to do that. So we just stop it here. So the next one is, say this term into this, then this term into that. So what will we get? So that is DB minus EA. So DB minus EA divided by D, this term. And if we do the next one, this term into this minus, so here you have that 0, so that means D into A0 divided by D, so that means here you would have A0. And if we just define that this term is equal to say F, so then the next one is F into E. So what we would have, that is F into E, next A0 into D, so that is minus A0 into D divided by this term, that is f. And now we have all zeros. That means if we proceed, then all the terms you would get zeros. And then the next one is, so if we say that this one is g, so the next one what you would have, that means this term, and here you have that 0, so that means here you can see that g into a0 divided by g, so that means we have a0 here. And we'll stop here because this is that a0, the lowest term in that polynomial, and this is the method we need to follow. So let me repeat once again. So that means whenever you have a polynomial like this, you have a polynomial like that, so just need to write the highest degree here, and then we need to write s5, s4, s3 like this, and the first row would be with that, start with the highest order. That means here it is s to the power 6, then a6, a4, a2, a0, all are the even polynomials. In the next row you have that odd polynomials, and always that multiplication is like this. So that means whenever you have say a, b, c, d, the multiplication is always like that. This first, that is cb minus dA divided by this c. So this is actually the rule we have followed whenever we build up this Routh table. And then Routh says that we need to just concentrate on the first column, of this particular table. So this is that first column. This is that first column of this table. You can see here. So this is that first column. First column of that table. And it says that the roots of the equation are all in the left half of the S-plane, that means all roots of this particular polynomial would be in the left half of this S-plane here. That means it would be stable if there is no change of sign in the first column. If all the elements of the first column are of the same sign, that means there would be no change of sign. So that means the first column. So we only need to concentrate on the first column and need to check whether there is any change of sign or not. So all the roots would be in the left half of that S-plane if there is no change of sign. And also it says the number of changes of sign in the first column is equal to the number of roots with positive real part. That means after forming this Routh table, we first look into the first column of this Routh table, and if we find that suppose n number of sign changes are there, that means n number of roots are in the right half of that S plane. That means those are actually unstable poles. So the changes of sign in the first column is equal to the number of roots with positive real part. That means those roots are actually unstable roots. That means that system has that number of unstable poles. So let me just summarize what we have done. So we started with this particular polynomial, and we are interested to see how many roots of that polynomial are in the left half of S plane or right half of S plane. And if the roots are in the left half of S plane, that means the system would be stable. So in last lecture, we have discussed about the necessary condition. So here we get the necessary and sufficient condition. And this particular method, that is that Routh-Hurwitz criteria, gives the necessary and sufficient condition for a class of polynomials where all the coefficients are constant, and here only the stability margin, that boundary, is that imaginary axis. And it says that first that criteria was proposed by Hurwitz, and it says that from this particular polynomial, if we just find some determinant which are called that Hurwitz determinant, so these all are the determinant D1, D2, like that, in number of determinants should be there, then all the determinants should be positive. So here it says that all the determinants should be positive. But finding or checking the positiveness of all the determinants is not so easy task. So then that Routh proposed one method, the tabular method, and it says that if we just make a table just following this particular multiplication method and that we have shown here, if we just form a table and if we look into the first column of that table, the number of the change of signs indicate that the number of roots are in the right half of the S plane. So if there is no change of sign, that means all roots are in the left half of S plane. That means that polynomial is a stable polynomial. All poles of that particular systems are in the left half of that S plane. So let us see one example. So we'll be taking one simple example. So this is one example. So suppose we have a polynomial that is, say, S cube minus 4s square plus s plus 6 equal to 0. So now the question is, if this is the characteristic equation of a system, then what would be the roots of that characteristic equation? That means the poles of that system. So we know the necessary condition. So the necessary condition is, this root would be, this polynomial would be a stable polynomial. That means all roots would be in the left half of S plane if all the coefficients are present and all of them are with same sign. So here you can see this is positive, this is negative, this is positive. So you can see that coefficients are not with same sign. So that means that necessary condition for stability fails. So that means it is unstable polynomial. Unstable polynomial means the roots of that polynomials are not, all roots are not in the left half of that S plane. So here if we apply the Routh-Hurwitz criteria, so how can we find? That means how many roots are there on the right half of that S plane. So the method is, we need to first write that S cube, then S square. You can see here this is that S cube, then S square, then S1, then S0. So the first coefficient is 1, this one, then you write all the odd coefficient first, because it starts with s to the power 3, and then you write this is 4 and this is 6. Here this is -4 and this is 6, and then multiply it. So that is -4 and minus of -6 divided by -4. So this value is coming 2.5, and here then this value is 0. Here the next this column, this element is 0. Then here you can see that 2.5, so that is 2.5 into 6 minus 0 into -4 divided by 2.5. So then we'll get 6 only. So this element is 6. So then we can see the first column. So in the first column we have 1, we have -4, we have 2.5, and we have 6. So this is actually that first column. So this is that first column. And here we can see that in the first column, if you see, so you have positive, you have negative, you have positive, again positive. So obviously there is a change of sign here. And how many changes of sign are there? So you can see here that positive to negative, and again negative to positive. So here positive to negative, and here again negative to positive. So basically, and here you can see that positive to positive. So the change of signs are here. Changes of sign. So how many? The number of changes of sign equal to 2. So that means according to the Routh-Hurwitz criteria, it says that 2 roots, here we can write that 2 roots are in right half of S-plane. So 2 roots are in RHP. As the number of change of sign is equal to 2, so 2 roots are in right half plane. So we can easily also see this one. So this polynomial, if you factorize that, so this factorization would give you that s minus 2, then s plus 1, then s minus 3 equal to 0. So we can see here s plus 3. So one root is 3, another root is 2. So 2 roots are on the right half of that S plane. So it is very interesting to see, and it is very powerful result in control theory. That means whenever a polynomial is given, so this is that polynomial, and without finding any roots, we can say how many roots are on the right half of that S plane, or all roots are in the left half of S plane. So that means if we just make the table, Routh table, like this, Routh table, and then if we just look into the first column of that Routh table, this is that first column, then the number of change of signs, is equal to the number of roots on the right half of that S plane. So let us solve one more example, and we can see that how this particular method can be used to design some control system as well. So here we are taking one system, that is, suppose this is that input, and here suppose you have a proportional controller, that is K. This gain is unknown, and you have one plant. So this plant transfer function is S, that is, so S plus 7 and then S plus 11. And now you have closed this loop, and you need to find what would be the range of K such that this system would be stable. And we assume that, so this is that negative feedback, we assume K is a positive gain. So now this is YS. So what would be the closed loop transfer function? So closed loop transfer function, that is ys by rs. So that is actually the forward path transfer function is k divided by s into s plus 7 into s plus 11. So if we just write that one, so that is gs. So if we say that this is gs, this is whole thing is gs, so then gs by 1 plus gs. So then if you write that one, you would have the closed loop transfer function, that is s cube plus 18s square plus 77s plus k. So now we are interested to find what would be the range of that k such that this closed loop transfer function would be stable. To be stable, we need to ensure that this particular polynomial, that is the characteristic polynomial, the roots of these polynomials all should lie in the open left half of the S plane. So how to do that one? So suppose we have that characteristic polynomial. So this is that characteristic polynomial in this case, which involves that k. This is equal to 0. We need to find what would be the value of k or range of k such that this particular polynomial would be a stable polynomial. All roots would be in the left half of the S plane. So let us apply Routh-Hurwitz criteria. So whenever we will be applying Routh-Hurwitz criteria, we need to start with that S cube, because this is that 3, then S square, then S, then S0. Then the first coefficient is 1 here, so this is 1, and then one gap, then another one is 77, and here S square, so this is 18, and next one is k. So now if we follow this particular multiplication, that is 18 into 77, that is 1386, and then minus k divided by 18. So now if you just again multiply it with this one, and this is 0 here, if you multiply it with that and divide it this one, so basically this one is k. So now you know that the first column here, you can see that this is that first column. This polynomial would be stable polynomial. This would be stable polynomial. That means all roots will be in the left half of that S plane if there is no change of sign. So as we have considered that k greater equal to 0, because we have already assumed that k greater than 0, so that means this particular term here, that should be greater than 0. So that means the closed loop is to be stable, if 1386, this particular term 1386 minus k should be greater than 0. So this implies that k should be less than 1386. So that means if k is less than 1386 and greater than 0, so if we allow this particular range for this k, this polynomial always would be a stable polynomial. That means all roots should be in the left half of that S plane. So from this particular example, what we have learned, that means whenever you have a closed loop system and suppose this k is a proportional controller, applying Routh-Hurwitz criteria and implying that imposing stability constraint, we can find the range of k for which that system would be stable. So now let us see what happens if we just put k equal to, so if k equal to 1386, then what happens if we just put k equal to 1386? So then in this case, if you look at the Routh-Hurwitz criteria, so what happens, we are again doing that one, so that is S cube and a square, then s, and we have s0. So then you can see it here. So this k value we have replaced with that 1386. So we can say that, okay, we have another polynomial, that is s cube plus 18 square plus 77s plus 1386. This is that polynomial. So then we can just make that Raoult table, that is 1 here, then 77, and for a square this is 18, and here 1386. So now you can see that means whenever you multiply it with this one, so that would be 1386 minus 1386 divided by 18. So that means it would be 0. So now this is actually one exceptional case where it might happen that one full row, and in this case this row, all elements, and in this case only one element is there, all elements in a row become 0. So if these things happens, then we need to follow a particular method to form the Raoult table. So in that case, you need to go one step above. So if you go one step above, then you have a polynomial that is called auxiliary polynomial. So this polynomial is with coefficient a square, so then it would be 18a square plus 1386. So this particular polynomial has a name which is called that auxiliary polynomial. And physically there is an interpretation of this auxiliary polynomial. Interestingly, it is found that whenever a particular row of a Raoult table becomes 0, and when we form an auxiliary polynomial like this, so this particular polynomial is actually the factor, is one of the factors of this original polynomial. So that means here you can see that this particular row becomes 0, then we need to go one step above and write one polynomial which is 18a square, and 1386, and it has that name auxiliary polynomial. And then we need to follow a method, that is we need to take the derivative of that auxiliary polynomial with respect to s. So if we do like this, then it would be 36s. Now take only this coefficient and replace here. So this is that method you need to follow. So that is 36. So in place of 0, you need to put that 36. And then again continue that Raoult table. So then again, if you continue that Raoult table, then what happens? This 36 into 1386, then here you have that 0. So 0 into 18, that is 0, divided by 36 means here you have 1386. And then you can see here one interesting thing, that is this polynomial that you have, this polynomial, auxiliary polynomial, this polynomial is a factor of the original polynomial. So that means the roots of this auxiliary polynomial are also the roots of this original polynomial. And here we can see that in the first column, if we look at here, in the first column, there is no change of sign. So no change of sign means we conclude that there is no pole on the right half of the S-plane. But here the scenario is little bit different, because in this case, this is actually one exceptional case. So in this case, we need to understand a particular, we need to consider a particular result, that is an even polynomial. An even polynomial, that means what is called even polynomial? For example, say s to the power 4, all coefficients, all the terms are with even power. So that means here, that is say s square plus 5, and here you can see that s to the power 0. So this is an even polynomial is a factor of the original polynomial. What is that? So when, so here, when a row of a route table is completely 0, when a row is completely 0, so then an even polynomial is a factor of the original polynomial. So in this case, you can see here, this particular row becomes 0. So then an even polynomial, so here you can see that this is that polynomial, auxiliary polynomial, this is that even polynomial, and this even polynomial is the factor of the original polynomial here, this one. And then there is one interesting property of an even polynomial, that even polynomial has roots symmetric to the origin. What is that? So that means if you take a complex plane, so here suppose this is that complex plane, so this is that real, and here you have that imaginary. So now this is that origin, this is that origin. So if you have a root here, so obviously there should be one complex conjugate root, and as it is symmetric to that origin, so then you can see here there should be another root here, and there should be another root here, and if you have a root here, then symmetric to this one, there should be another root here. If you have one root here, then symmetric to this origin means you would have another root here. So this is actually the property of one even polynomial. That means all roots are actually the symmetric to the origin. So now what happens here? Here actually this is that auxiliary polynomial 18a square plus 1386, and this part of the route table says about the roots of this particular even polynomial. So now just try to understand this particular fact, that from this term to this term there is no change of sign, and when there is no change of sign, that means for this particular auxiliary polynomial, which is an even polynomial, it does not have any root on the right half of that S-plane. And now you just apply this particular property of even polynomial. So since there is no roots on the right half of that S-plane, as the roots are symmetric to that origin, that means there should not be any roots on the left. So then what happens? This particular polynomial is one even polynomial with order 2. That means it has two roots, and as no roots on the right half of that S-plane or left half of that S-plane, that means two roots would be on the imaginary axis. That means this type of things happen. Two roots on the imaginary axis, and it should be symmetric to the origin. So let us write it here that for this particular example, so no roots in the right half of S-plane. The reason is there is no change of sign, no change of sign. As there is no change of sign, then no roots on the right half of S-plane, and as the roots are symmetric, then no roots would be on the left half of S-plane as well. So two roots would be on the imaginary axis. So no roots in the left half of that plane, since they should be symmetric with respect to origin. So then what happens? Two roots, that we would have two roots on the imaginary axis. So in this particular example, what we have seen, that means if we just take this particular polynomial, and from where we get it, we just took that k equal to 1386, and then we are just trying to find what would be the roots of this polynomial. Then we find that one of the row becomes 0, and whenever one of the row becomes 0, according to the Routh table method, you need to go one step above and need to write one equation. So this equation is called a polynomial. This polynomial is called that auxiliary polynomial, and then we need to take the derivative of that polynomial and then take this coefficient and replace it here, and then again proceed. So if we proceed and complete that Routh table, then we find that in the first column there is no change of sign. But the interesting point is, whenever you have a row completely 0, so when a row is completely 0, it means an even polynomial is a factor of the original polynomial. And now we have seen that even polynomial has roots symmetric to the origin. So these things happens. So then in the Routh table, we find that from this particular point to bottom, it indicates the roots of the even polynomial. And as there is no change of sign, so no roots in right half plane, and according to the symmetry, then there should not be any root on the left half of plane. But as the polynomial is a square polynomial, so that means it has two roots. So the rest of the roots means only two roots would be on the imaginary axis. And now if you look at that polynomial, so this is a third order polynomial, so it has three roots. So we find that two roots on the imaginary axis, and this particular part, if you see that in the first column it is positive, second column also positive, so that means there is no change of sign. So that means one root is in left half of S-plane and two roots on the imaginary axis. And here, if we just take that auxiliary polynomial, that is 18s square plus 1386 equal to 0, then we can find that s square equal to minus 1386 divided by 18, that is 77, and you have two roots, that is plus minus 8.77j. So then you can see that two roots of this polynomial, it has roots on the imaginary axis, which is clear from the Routh table. And interestingly, these are also the two roots of the original polynomial. And we can also get some more information from here. That means, as we know that omega equal to 2 pi f, that is 2 pi by t. So this omega is here, you can see that 8.77 rad per second, that is that rad per second angular frequency. So then the time period that you would have, that is 2 pi by 8.77, so that is 0.716 second. So that means if we go to this particular closed loop system, and in place of k, if we put that 1386, that means if we put that k equal to 1386, then we find that that system would be purely oscillatory, and that for that oscillation you can see that angular frequency that you would have, that is 8.77, and the time period would be 0.716 second. So it is very interesting to see, that means the various parameters as well as the performance of that system as well as that stability for a closed loop system using this Routh-Hurwitz criteria. So let us take one more example, that is what happens if we take that, determine the stability of the closed loop transfer function. So suppose a transfer function is given, that is Ts equal to 10 divided by that 5 plus 2, 4, 3s cube, 6s square, 5s plus 3. So if this is the closed loop system, we need to determine the stability. That means this is that characteristic polynomial. So we can write the characteristic polynomial. So this one would be equal to 0. So now we'll be applying that Routh-Hurwitz criteria. So then it starts with that s to the power 5, and then s to the power 4, s to the power 3 square, 1, s to the power 0. So the first coefficient is 1 here, that is 1, then 3, then 5, and here you have 2, 6, and 3. So now if we follow this particular multiplication rules like this, so that would be 6 minus 6, so 6 minus 6 by 2, that is equal to 0, and here we have 2 into 5, that is 10 minus 3 divided by 2, so that is 7 by 2. So now you can see one thing, that means whenever the first element becomes 0, then we cannot proceed, because in case of Routh table, you need to multiply with this term with that term, and then need to divide by that first term. So whenever it becomes 0, then how to proceed? So this is that another case what we face in Routh-Hurwitz criteria. That means 0 appears only in the first column. So the other case what we have seen, that means whenever we'll be making Routh table, it might happen that a full row may become 0, but in this case only the first element may be equal to 0. So then we need to replace that element by a small number epsilon. So replace this element by a small number epsilon. So then if we proceed it, then what we would have, that is 6e, we have that 6e, then minus 7 divided by epsilon, and the next one is epsilon into 3, that is 3 epsilon minus 0 by epsilon, so that would be equal to 3. So again, if we follow this one multiplied with that and this one with this divided by this one, so you would have that 42 epsilon minus 49 6 epsilon square divided by 12 epsilon minus 14. And now if you multiply with this one, and here you have 0, so this one divided by this term, that means you have only 3. So this is that Routh table, and you can see that this is that first column we have. This is that first column. So now what we can see, that the level, so level is S5, S to the power 4, S3 square, S and S0. And whenever epsilon equal to positive, it is a small number, and we can also take epsilon equal to negative. Then you can see that whenever epsilon is positive, this is epsilon free, so that is positive number 1, and then S4, this is again positive number, and here we can see that this is positive, and whenever this is a very small number, then this would be 0, so that means it would be negative. And here we can also see that this term, say almost 0, and that would be positive, and here this is positive. And whenever we take that negative here, negative, so then the first one is that positive, and then second one is also positive, but here you can see it is negative, so then that is negative. And whenever this is negative and this is negative, so negative, that means it would be some positive. And then here this is negative, again that would be negative, so all negative, so then that would be positive, and this is positive. So that means here we can see that this is the first column where we have the change of sign. We can see here, that means, so no change, but here you have a change, and you can see here again you have a change. So here no change, and in this case no change, here you have a change, and here again you have a change, no change. So if you take positive or if you take negative, in both cases you can see that there are two changes, sign changes in the first column. So two sign changes in the first column, so that means two poles. So here you can see that two poles in right half plane. So this particular method is called that epsilon method. So when the first element, when the element in the first column, when the element in the first column becomes 0. So in that case, we need to replace that element by a small number epsilon, and then we need to follow the same method for building up that route table, and then we'll be looking at the first column of that route table, and then we check the number of change of signs, and the number of changes is equal to the number of poles in the right half of that S-plane. So in this particular example, we found that there are two changes. If we go with epsilon equal to positive, so two changes are there, and if we go with that negative, again two changes are there. Then you may ask questions that always it would happen. No, sometimes this particular method fails. So particularly whenever the polynomials have all the complex poles, imaginary poles, purely imaginary poles, so in that case this epsilon method may fail. So this method, in some examples it fails, so in that case that reverse order method. So reverse order method means if we change that polynomial, that coefficients of that polynomial in the reverse order, that means if we bring 3 here and 3 here, so 1 here, then we replace 5 here and 2 here, then 6 here and 3 here. That means if we reverse that coefficients in the polynomial and if we build that route table, so sometimes that helps to find how many poles are on the right half of that S-plane or in the left half of that S-plane. So let me just summarize what we have discussed. So today we have started with that Routh-Hurwitz criteria, and this particular method is used to find how many poles are in left half of S-plane or right half of S-plane. That means the boundary is that imaginary axis, and it has some limitations. So one of the major limitation is the polynomial should have with real coefficients, and the second one is it gives the necessary and sufficient condition. That means all Hurwitz determinants should be positive, but for finding whether Hurwitz determinants are positive or not, so we follow that Routh table, and in the Routh table method we have seen how to make that table, and then we need to look at the first column of that table. The number of sign changes indicates how many roots are in left half of or right half of S-plane. That means number of sign changes is equal to number of roots on the right half of that S-plane. And if there is no sign changes, that means all roots are in the left half of S-plane. And then we have seen some examples, and there are two different cases we have seen. One case is all elements in a row may become 0. So in that case, we need to form that auxiliary polynomial, and for finding roots of that auxiliary polynomial, we have invoked the property of even polynomials, because in this case, even polynomial would be a factor of that original polynomials that we have seen. And the other case, what we have seen in Routh-Hurwitz criteria, that means the first element of a row may become 0. So in that case, we need to follow that epsilon method, but we found that this epsilon method sometimes may fail, particularly whenever the polynomial has all the imaginary roots, and in that case we can avoid that method just by changing that coefficients of that polynomials, just swapping that polynomials. So that method I am not going to discuss here. And in the next class, I will be solving one problem on that even polynomials. Then I will start that time domain analysis. Thank you.